Hello friends, a very happy morning to all. I believe you all stay safe and healthy. Myself Ram Kumar, Assistant Professor in the Department of Mechanical Engineering, and I welcome you all for this online webinar session organized by our department. It is my great pleasure in sharing a few words about our college and our department. Francis Xavier Engineering College is popularly known as FX Engineering College, which is located at the heart of Tirunelveli city, and it was established in the year 2000. FX Engineering College comes under the SCAD group of institutions. Our institution has been offered autonomous status in the year 2019. We offer 6 EG programs, 10 PG programs and research centers. Our college has achieved many awards. Among all, I would like to list a few to your knowledge. We got Gold category for Industry Linked Technical Institute, which was awarded by AICTE CII survey. In Chronicle Engineering College survey, we achieved 3rd position among 19 engineering colleges in India. In Times Best Engineering College survey, our college has obtained 15th rank in Tamil Nadu and 108th rank in India. Apart from all, we got ICT Academy Tamil Nadu Academic Partner Excellence Award in 2017. Regarding the Department of Mechanical Engineering, it is the largest department on campus with 600 plus students, 35 faculty members and with good infrastructure facilities. We offer BE in Mechanical Engineering and ME in Industry Safety Engineering. The UG program was accredited by the National Board of Accreditation. We have FANUC Center of Excellence for CNC Center, BMW and Hyundai supported mechanical labs. Our department has signed many MOUs with the leading manufacturing and service industries. Apart from regular academic activities, our students have been trained and imparted with various skill training programs and value-added courses. The special feature of our department is the establishment of 3 applied laboratories in addition to the regular labs. The purpose of these labs is to inculcate the student with innovative skills which is required by the industry. We offer international certified program in CAD and NDT. We have also organized many international conferences, workshops and funded seminars. I hope the session will be more useful for all of us. Thank you.
Hello everyone, this is Maheshwari, Assistant Professor in Department of Mechanical Engineering, Francis Xavier Engineering College, Tirunelveli. It is my great privilege to introduce our resource person, Dr. M. Udayakumar, Professor in Department of Mechanical Engineering, National Institute of Technology, Tiruchirappalli. He completed his undergraduate in Mechanical Engineering from Government College of Engineering, Salem. He completed M.Tech in Thermal Sciences from IIT Madras. He completed his PhD at Bharathidasan University, Trichy. He worked as a development engineer in various industries from 1982 to 1986. After that, he started his teaching career in National Institute of Technology in the year 1987. He has more than 25 years of academic and research experience. He is serving as a distinguished author for many high-impact research articles, reviews, book and book chapters. He has been loaded with many responsibilities in the department and rendering consultancy services for various educational institutions and industry. He is the recipient of many research funding from government and private bodies and has immensely contributed for the establishment of new research and academic laboratories for the Department of Mechanical Engineering. He is a certified energy auditor and safety auditor. We are proud to invite such a proud person to this webinar session. I welcome you all for this session. I wish you a great learning. Thank you everyone, and over to the speaker, Dr. M. Udayakumar.
Hello? Yes, my voice audible? Yeah, slide is visible. Fine. Good afternoon. Today I'm going to present you a seminar on testing of IC engines. particularly with the fuel prices, namely diesel price reaching about 80 rupees per liter. Many of the automotive users find it extremely difficult to meet the fuel cost, because over the past year or so, the prices have gone up by more than 25%. And with the lockdown and no opportunity to make good livelihood, giving jobs, it's rather very difficult for people to meet this fuel bill. And under these circumstances, if our engines or automotive engines or stationary engine, whatever it is, if these engines perform not as per the designed conditions or as per the manufacturer's condition, data conditions, then naturally we are going to lose a lot. So it's very important for us to conduct the tests on engines, not only after the maintenance works are carried out, but periodically also, to ensure that the engines are running with the best, running with giving us the best performance. So when you say performance, we should get both power at the rated conditions as well as the efficiency should not be, the efficiency should be as per the nameplate details. So it becomes important for us to periodically test the engines. And this testing of engines is to be done even by the service people. When they overhaul the engine, then only they can ensure that, or they can convince the client or customer that after repairs or after maintenance, the engine is delivering the best performance with the desirable efficiency. So testing is very much important. Now, these IC engines testing involves both SI engines, namely the spark ignition engines are loosely known as petrol engines, as well as compression ignition engines are loosely known as diesel engines. Both types of engines are used both in automotive applications as well as in stationary applications. So we have to test these engines irrespective of the fuel used. And these engines testing involve measurement of the two following important quantities. Number one, the torque delivered by the engine at the given speed. Number two, the power which is produced at the given speed. And in addition, we should ensure that the efficiency is high. So we should measure the fuel consumption. So we are conducting the tests on petrol engines as well as diesel engines in a test rig where these quantities are measured. Of course, it is important to measure the emissions also. And for that, sophisticated instruments are needed, and in many places we don't have the emission measuring instruments. And particularly for automotive engines, there are centers where they conduct the tests and certify whether emissions are under check or emissions are under control. So they give a certificate for a given fees. So we can ensure that the emissions are also well within the stipulated limits so that our engines or vehicles are not polluting the atmosphere beyond the specified limits. In addition, if you are in research or if you are in engine manufacturing organization and an engine assembly organization for an automotive manufacturer, it is important for us to conduct the heat release tests and obtain the data which will give you a lot of information as to whether the engine is knocking or whether the engine is having excellent combustion efficiency. So either the indicated thermal efficiency, which is a measure of the ability of the engine to convert the fuel chemical energy into useful thermodynamic work. So these quantities are determined in research laboratories and in engine manufacturing centers and in automotive assembly units periodically to ensure that the engines are really performing as per the designed conditions. Now, before going into the testing of engines, let us see, maybe some of the audience may not be familiar with the terminology which we are going to use. So briefly, we will see there are different types of engines and their working principles, etc. So essentially, we have in an IC engine, whether it is petrol engine or diesel engine, we have yeah, reciprocating piston type engines. Inside the cylinder, the piston reciprocates, and the cylinder head has the passages through which the fresh charge can enter, as well as the burnt products can leave. So the port or the passage through which the fresh charge entering is known as the inlet port, and it is opened and closed by an intake valve, which is operated by a cam, which is driven by the camshaft. And this camshaft runs at half the engine crankshaft speed, so that in a four-stroke cycle engine, I'm talking about a four-stroke cycle engine. In a four-stroke cycle engine, we have for every 2 revolutions of the crankshaft or the engine shaft, only once the inlet valve will open and close. And as the inlet valve opens and closes, at that time, the opening is synchronized with the movement of the piston from the top position to the top position till it reaches the bottom position. And this synchronization is done with the help of what are known as cam, which in turn is attached to the camshaft, which runs at half the crankshaft speed. Similarly, the exhaust valve opens when the combustion process is completed and the products are to be expelled out. So now you see the exhaust valve is opening and the products are going out till the piston reaches the top dead center position. So when the piston moves from bottom dead center to top dead center, the exhaust valve remains open. And when the fresh charge is to enter, as the piston moves from top dead center till it reaches the bottom dead center, the fresh charge is entering. During the compression stroke and during the power stroke, both the valves remain closed. Now, this is the principle of operation of a four-stroke cycle engine. And we have in the cylinder head, we have a spark plug provided. And the function of the spark plug is to give the spark ignition energy needed to initiate the combustion at the end of the compression stroke. So now what we are seeing is suction followed by compression. Now spark energy causes the power. Now the exhaust happens and again the next cycle starts. So this is how an SA engine operates. In the case of a CA engine or diesel engine, instead of the spark plug, we will have a fuel injection device known as nozzle, which in turn receives pressurized diesel from a fuel pump, and that fuel is injected as the piston reaches the top dead center position. And the air which alone is entering during the suction stroke in a diesel engine is compressed to higher temperatures and pressures. The fuel injected thus catches fire spontaneously and it gives the power stroke. So you don't require any spark plug as far as diesel engines are concerned. Otherwise, the operational principle of the operating parts, the components present in a petrol engine and diesel engine are almost the same, except for the fuel injector and spark plug, as the case may be in diesel and petrol engines. Now, the outline of this presentation, I have given many topics, but let me not go into all the topics because we have to focus on testing. We'll briefly see the internal combustion engine terminology, the difference between petrol diesel engines, operating and working cycles, then performance of engines. This is what we will see. So let me move to the next slide. So this slide is not important to us because it gives historical aspects of how the engine got developed, so on. Now, this is also not so important. But heat engines are the engines which convert the heat into work, and accordingly, a device which operates in a thermodynamic cycle, absorbing heat from a high temperature body and rejecting heat to a low temperature body. In that process, producing net positive work is a heat engine. Thermodynamically, this is defined. Now, to this classification, to this definition of heat engine, we can have external combustion engines as well as internal combustion engines. IC engines normally are reciprocating type engines or rotary engines. Now, internal combustion engines, as we have seen in the first illustration, receives the charge into the cylinder, burn the fuel inside the cylinder, and the heat produced is getting converted to work in the form of a rotation of the crankshaft at a particular speed, and the torque delivered multiplied by the angular velocity at which the shaft is rotating give us the power produced. But as far as external combustion engines are concerned, they also belong to the heat engine definition only, but they use the heat from an external source. Nothing is burnt inside. For example, in steam power plants or in steam engines, steam is produced elsewhere. Fuel is burnt in a furnace and the steam is produced in the boiler. And the produced steam is used to drive the steam engine or turbine. So now combustion happens in the working fluid. But in the case of turbine engines, steam engines and turbine engines, again steam is being used. Or we may go for a heat source. We may go for a heat source like heat produced in a nuclear reactor, which in turn is used to produce steam and so on. Now, even the internal combustion engines can be classified into rotary engines and reciprocating engines, of which these rotary engines are particularly the gas turbine engines are rotary engines where the combustion happens within the engine proper, gas turbine engine proper. We will not go into that. Now, coming to this reciprocating engines, as I just now told you, CI engine is loosely the diesel engine, SA engine is the petrol engine, and both CI engine and SA engines can operate in 2-stroke cycle or 4-stroke cycle. 4-stroke cycle is one which we saw just now, namely piston moving from top dead center to bottom dead center during suction stroke. When the inlet valve remains open, charge flows from the atmosphere. The atmospheric air flows through the filter and then it enters the carburetor, or it passes through the butterfly valve into the inlet manifold port. And in the case of fuel injection engines, multi-point port injection engines or port injection engines have fuel injectors through which the petrol is injected. So the air which is entering mixes with the fuel, it enters the cylinder during the suction stroke. This is the first stroke. At the end of the suction stroke, the inlet valve close. Already the exhaust is open, closed. So when the piston moves from BDC to TDC, compression happens. And at the end of the compression stroke, a spark is initiated with the help of a sparking arrangement, and a small flame is formed, and this flame starts traveling towards the unburned fuel air mixture present in the cylinder at high speeds, and the reactants are getting converted to products, and thereby heat is released. The heat released causes a rise in pressure in addition to rise in temperature. So this pressure pushes the piston down in the power stroke. And as the piston comes down in the power stroke, before it reaches the bottom dead center, we open the exhaust valve so that the exhaust stroke can commence with a relatively less resistance, and the products of combustion can go to the exhaust pipeline and through the silencer to the atmosphere. That is as far as the SI engine is concerned. In four-stroke SI engine is concerned. In CI engines, as I already told you, only air is entering, and instead of fuel air mixture, we are giving only air, and the fuel is injected at the top dead center at the end of the compression stroke. The fuel undergoes atomization, vaporization. It mixes with the air to form a combustible mixture, and because of the higher compression ratio, the temperature is higher than the auto ignition temperature. So the injected fuel, which forms the mixture, catches fire spontaneously, or it auto ignites. So due to this auto ignition, the reactants, fuel chemical energy is released as heat, and this heat raises the pressure, and the piston is pushed down in the power stroke. So there's a main difference. There's a main difference between SI engines and CI engines. Now, the various parts of the engine are shown in this illustration, which of course for mechanical engineers is very well known. So I'll not go into that. So as I just now told you, the components in a particular cylinder, one cylinder are, these are the valves. So this is exhaust and this is inlet line, exhaust line. And these valves are operated by cams, which in turn are driven by camshafts. And the camshaft in turn is driven by the crankshaft using a timer belt or using a timing gear. You have the piston reciprocating inside the cylinder. You have the connecting rod. The connecting rod is connecting the piston pin with the crankshaft, and you have crankshaft web for better balancing. And as the crankshaft rotates, you have the piston reciprocation is getting converted to rotation of the crankshaft. So when we do the testing, what exactly we are doing is we are trying to apply a braking torque to the crankshaft. So when you try to brake that, so naturally the piston has to overcome the braking resistance, and for that it has to consume fuel, and the fuel is supplied through the supply, and the fuel is supplied through the supply line as far as the SI engines are concerned. If it is diesel engines, it is injected in varied quantities through the injector. Now, to do the testing, we have to have some knowledge of the various terminology associated with the engine so that we are able to conduct the test properly. The terminology associated with the IC engines are: bore is the inside diameter of the cylinder, stroke is the maximum distance traveled by the piston, which is equal to twice the crank radius. The crankshaft radius is known as twice the crankshaft radius is stroke. The top dead center is the topmost position to which the piston can move. VDC is the bottommost position to which the piston can move. Between these two limits only the piston will reciprocate. Stroke volume or swept volume is the volume displaced, which is equal to pi by 4 into d square into the stroke length L. Now that's what is shown here. And compression ratio is defined as the ratio of the volume of the cylinder at BDC to the volume of the top dead center, which in turn is nothing but the swept volume plus the clearance volume divided by the clearance volume. Now for petrol engines it varies from 6 to 10. Mostly it's close to 10. In diesel engines this value varies from 14 to 20. Generally it's 16 to 20 in most of the cases. In fact, it can even go to 24 as far as three-chamber engines are concerned. Now, this compression ratio is one of the design parameters, because when you design an engine, you have to fix a particular compression ratio. So it's a design parameter. Similarly, the piston speed is mean piston speed. Mean piston speed is nothing but average piston speed, which is equal to 2 into L into N, where L is the stroke length, N is the revolutions per second, RPS, or I'm sorry, N here is RPM, revolutions per minute. You divide it by 60, so it becomes RPS. So this is again a design parameter. So an engine designer takes into consideration certain parameters with which he designed the engine. The parameters considered are, as I have shown here, compression ratio, then mean piston speed, brake mean effective pressure, and SFC. Brake mean effective pressure is, we will see later what is brake mean effective pressure. So this I will skip because already I have told you. Now coming to the operating cycles of these engines, Carnot cycle is the ideal cycle, and this cycle gives the highest thermal efficiency. However, in practice in IC engines, it is impossible to realize. So we don't go for Carnot cycle in IC engines. Instead, in SA engines or petrol engines, Otto cycle is what is the ideal cycle, where you have a reversible adiabatic compression followed by constant volume heat addition, reversible adiabatic expansion followed by constant volume heat removal process. So the area enclosed by this cycle 1, 2, 3, 4 is the ideal work produced by the working fluid during an Otto cycle. And the efficiency of this cycle can be using thermodynamic relations calculated, and it is found to be a function of only the compression ratio. Similarly, the diesel cycle has, which is the ideal cycle to represent the working of diesel engines, as reversible adiabatic compression process followed by constant pressure heat addition, reversible adiabatic expansion process followed by constant volume heat removal. And this cycle is having slightly lower thermal efficiency for a given compression ratio compared to Otto cycle. However, this cycle is preferred when you have your ability to increase the compression ratio is more. So in diesel engines, the compression ratio is increased, and accordingly, for the same quantity of heat add, we can get more efficiency. So here, the efficiency of this as standard cycle depends not only on the compression ratio, but also on what is known as the heat addition cutoff ratio. So these two parameters determine the efficiency of a diesel cycle. Then you can have dual cycle where you can have part of the combustion happening in constant volume and part happening in constant pressure process. Now, in two-stroke cycle engines, all the four events are completed. Suction, compression, power, and exhaust are completed in one revolution of the crankshaft, whereas in four-stroke cycle engines, we require two revolutions to complete one cycle. Now let's not go into this. We have to focus only on testing. Okay. Now coming to the testing, the test bed comprise of this. You would have seen in your institution thermal laboratory an engine which is connected to a dynamometer through couplings, and the exhaust gas line is to the exhaust gas line. We have connected a probe through which the sample is taken and the exhaust gas is collected and analyzed, or the amount of exhaust gas constituents during a given testing is indicated by this instrument number 2 during the testing. Then we measure the fuel flow by using a volumetric fuel flow device, namely a burette, to which we measure the time it takes for 10 cc of fuel to be consumed. In addition, we can measure the airflow rate also, so that we will know the volumetric efficiency of the engine, and also we will be able to conduct the heat balance. And this dynamometer is a loading device with the help of which we are able to apply the braking of the rotating shaft of the engine. So as you apply the brake, the engine tends to overcome the applied braking torque, and accordingly it produces that much amount of torque by consuming fuel. So you measure the braking torque and the speed you measure. So you know the torque and you know the omega. So the power produced is known. And different types of dynamometers are available with which the torque, and using a tachometer or using other sensing devices, we can measure the speed. So the dynamometer essentially comprises of a load cell which measures the braking torque, and the tachometer which gives us the speed. Then to control the braking, we have controlling devices. This dynamometer could be a simple brake drum dynamometer, or it could be eddy current dynamometer, or it could be even an electric generator. In addition, we can measure the rotational speed, as well as we can measure the crankshaft position by using a toothed wheel and using a sensor. It is possible for us to measure if you have 360 teeth on the toothed wheel, then for every one rotation of the crankshaft, you will get 360 pulses. But these pulses can be captured as the engine runs. Simultaneously, using a transducer, normally pressure transducers made up of quartz elements are used in engines. So the piezoelectric transducer gives a charge due to change in pressure, and that charge is converted into voltage using a charge amplifier, and that voltage in turn is communicated to the data acquisition system. So there it is possible for us to match the pressure at each and every crank angle position of the piston, and accordingly we can get the pressure volume plot of the engine. And this pressure volume plot is very useful to get the indicated work per cycle, can get the indicator diagram, and also Using the thermodynamic analysis, it is possible for us to get the heat release per cycle, how much heat is released. So from that we can even determine the combustion efficiency and so on. But this is what is done in most of the engine manufacturing units and in the engine assembly factories. So they have to ensure that the combustion efficiency is high and the rate of pressure rise are within the limits so that the life of the engine is ensured. So this type of test rig is what is used to conduct the tests. Oh, when you conduct the tests, what are the efficiencies that you determine? You determine the mechanical efficiency. The mechanical efficiency is the ratio of brake power to the indicator power. What is brake power? Brake power is the product of the torque developed at a particular condition and the angular velocity omega. 2 pi n by 60 is omega. So you run the engine at steady state conditions, namely at a constant torque and at a constant speed, and measure the fuel consumed under steady state conditions and calculate the brake power. Now, indicator power is given by the indicator diagram, and the indicator diagram is having a length equal to L, and rather it's not the indicator diagram, rather the indicator diagram is having an area, and this area is having the ordinate as indicated mean effective pressure, and L into A is nothing but the volume per cylinder. Now, when you have n number of cylinders, k number of cylinders, then the k should be included. And n is the rotational speed and RPM. So, the indicator power is calculated from the indicated mean effective pressure. Now, the ratio of this brake power to the indicator power is the mechanical efficiency. This we normally calculate in our IC engines lab. First, by plotting the total fuel consumption in the y-axis for different brake power values. So you'll get a linear curve, but it will not start from the origin, but it will have a offset. Now, if you extrapolate this curve to meet the negative x-axis, what you get is the intercept known as the frictional power. Or unless you give that much of frictional power, the engine cannot run at the given speed. So that much of power is known as the frictional power. So that frictional power is added to the brake power to get the. But with the pressure transducer and a crank angle encoder and using a data acquisition system and analysis, it is possible to get the indicator power accurately. Thermal efficiency. The thermal efficiency is given by, it could be based on indicated power or it could be based on brake power. The indicated thermal efficiency is given by the ratio of indicated power to the heat supplied. So indicated power is in kilowatts and MF is the mass of fuel supplied in kg per second, and the calorific value is the heating value of the fuel in kilojoules per kg. Similarly, the brake thermal efficiency is calculated using this relation, brake power by MF into C. Now, the mean effective pressure is calculated as follows. The indicated mean effective pressure is given by 60,000 into IP by LA N into K. It should be capital N actually, where N is the RPM. K is the number of cylinders. The brake mean effective pressure is given by this. I told you earlier that the brake mean effective pressure is a design parameter. Now let us assume your company or your organization builds a engine which is to deliver say 850 kilopascal of brake mean effective pressure. And unless that engine which is built with the steel, cast iron, aluminum and other components, various components and proper manufacturing good practices are followed, excellent material identified, still when you assemble all the components and with the proper lubrication and when you do the running, you design the engine to give, let us say 850 kilopascal mean effective pressure. But if it gives only, let us say 800 kilopascal, well, that is the maximum possible. That is what is realizable actually. Right? Now, this realizable value, brake mean effective pressure into number of cycles per second is the brake power that you are going to get, multiplied by the swept volume. So the volume of the cylinder multiplied by the brake mean effective pressure into the number of cycles per second is the actual brake power you are going to get or you are getting. So this is the power you are getting. Fine. Now, after some time, after maintenance work, if you are unable to get this much of power, then you are not having a good engine. Rather, with the fuel prices being what they are, you are getting subpar performance or poor performance. So naturally, it is time for you to decide whether to renovate the engine or repair the engine, or even after repairs, you are unable to get the better performance. Maybe it's time to scrap it and go for a brand new one. And as you are aware, continuously improvements are happening in the material science and in manufacturing processes. And because of which, we find that an engine which was manufactured 10 years back is certainly far, far inferior to an engine which is manufactured in the present day because of the improvements in the various manufacturing practices and in the availability of better materials. So you should not insist that this engine is 40 years old and it is giving excellent performance. Sentimentally, I am attached like that. It's because it will lead to wastage of our resources. So you have to conduct the test periodically, say at least once in a year, if no damage is being caused or if maintenance is being carried out under periodic maintenance conditions. Then also you have to conduct the load test to ensure that your engine performance, namely the brake mean effective pressure that you get, is not deviating very much less from the designed value. And the reciprocal of, this is as far as the power produced is concerned. Similarly, the fuel consumption is to be measured for the given power production. So that quantity is known as a specific fuel consumption or brake specific fuel consumption. This brake specific fuel consumption is nothing but the mass of fuel consumed in kg per hour for the given power being produced under steady state conditions. Now, if this SFC value is higher than the nameplate value of the engine or the manufacturer's claimed value, then your engine is unable to convert the fuel chemical energy into useful work properly. So it is inefficient. So it is time to improve the efficiency by carrying out the maintenance activities. If still with the maintenance activities, your SFC is not improving, means then it is time to scrap it or go for a better engine. So these are some of the tests that are conducted, namely the fuel consumption test, which leads to measurement of SFC, load test, which gives us an idea about the mechanical efficiency, which is a measure of the friction associated with the engine, and the brake mean effective pressure, which is a measure of how well the engine is converting the fuel chemical energy into brake power or useful power. So that is how we conduct these tests, and these tests are to be periodically conducted, irrespective of whether the engine is running or not, to ensure that we are not losing the resources which are procured at very high cost, namely the fuel like petrol and diesel. I think with this we can stop. Hello, Robinson?
Okay. Sir, thank you so much, sir. Thanks a lot for your nice and wonderful presentation. It was very informative and very useful to us, sir. Thank you. Now, questions session, sir. Some questions from participants.
Sure.
First question from Dinesh Babu. What are the safety precautions we should follow while testing IC engine with hydrogen fuel?
Well, the problem with hydrogen fuel is that it is having the maximum heating value per unit mass, and also it is very light, and the flame velocity associated with hydrogen is the maximum. Because of this, we have to ensure that there is absolutely no leakage of gas anywhere. If in any of the connecting pipelines, threads or joints, or in the nozzles through which you are metering it, or the valves through which you are controlling the flow, if there is any fine leakage, that can result in a very heavy catastrophic accident. So you have to be very, very careful. So leakage is the most important thing. Leakage arresting is the most important thing. Secondly, metering. Metering in the sense, you should first of all calculate how much of fuel is to be supplied, hydrogen fuel is to be supplied per cycle. The engine is designed either for petrol operation or for diesel operation, right? So whether you want to operate at 100% rated load or whether you are going to operate at sub-rated peak power, you should decide first. Secondly, based on the fuel and in comparison with the hydrogen's calorific value, you should arrive at the volumetric flow rate of the hydrogen to be supplied in metered quantities. And then also you should have the pressure regulator in such a manner that at constant pressure from the hydrogen cylinder, the flow is regulated, reduced to close to atmospheric pressure, and then you are able to effectively mix it with the charge which is entering into the cylinder. So most important thing is improper calculations will lead to, if excess hydrogen goes, you will have a blast. You will have a catastrophic accident. So a lot of calculations are to be done before you start your experiments, and your controlling quantities or metering orifice, metering valves, and the hydrogen source, all those are to be properly chosen. Finally, you have to have perfectly leak-proof arrangement.
Okay, thank you, sir. Sir, next question from Janani, sir. What are the effects of volumetric efficiency on combustion temperature?
Yeah. Volumetric efficiency actually reduces the, rather, lesser volumetric efficiency means when volumetric efficiency is 100%, absolutely no problem. Unfortunately, 100% volumetric efficiency is impossible in any engine, particularly in four-stroke engines. The volumetric efficiency best you can get is close to 80% only. Even that is very difficult. Only in the case of turbocharged engines, you will get higher efficiency. But in naturally aspirated engines, if you get 80%, you are lucky. Sometimes it is as low as 60%. And because of this volumetric efficiency, the charge that is entering is less. So the amount of fuel that you can burn gets reduced. So that's the biggest problem. So when fuel burns, the adiabatic flame temperature will be reached. So temperature is not at all the issue. It is your ability to burn sufficient quantity of fuel air mixture within the cylinder that is compromised when volumetric efficiency is low. Temperature is not an issue.
Okay, thank you, sir. Sir, next question from Sunil Kumar. What is the difference between BS4 and BS6 standards?
It is essentially about the amount of sulfur that is present, because the pollution created by burning the fuel in engines is phenomenal. In Delhi, we are unable to live in the months for 6 months. From October to March, it is almost impossible to walk out in the morning or even the evenings, because the air quality is so bad. And the biggest contributor for such a poor air quality is, number one, particulate emissions caused by diesel engines, and the sulfur dioxide released due to the burning of sulfur in the fuel, and nitric oxide emissions. In petrol engines, we have catalytic converter, which ensures that nitric oxide emissions are three-way catalytic converter. When you have NO is restricted, carbon monoxide also is reduced. However, the sulfur, no catalytic converter will capture. It simply comes out as sulfur dioxide, and it is a respiratory irritant. Similar in case of diesels, till about 5-6 years back, our fuel quality was so bad because our refineries want to source the crude from the cheapest suppliers, and such crudes are known as sour crudes, SOUR, sour crudes, and these crudes have a lot of sulfur, and this sulfur content is not reduced in the refinery earlier days. Of course, now they have installed in most of the refineries desulfurization plants at a very heavy investment. More than 40,000 crores have been invested in those plants to remove the sulfur. And the BS4 used to have about 0.5% of the sulfur by mass in the fuel. But under BS6, the sulfur content has been far more reduced. Now it's in terms of parts per million only. It is not in percentage. So the fuel is clean. So when the fuel is clean, naturally the pollution cost is also very much reduced. But in spite of that, in diesel engines, the nitric oxide emissions are very high, because nitric oxide emissions is purely dependent on the flame temperature, the combustion temperature, and with high compression ratios and modern diesel injection systems being available, the efficiency is improved, but the temperature of operation has gone up, and the adiabatic flame temperature has slightly increased. And this results in more amount of NOx produced. And nitric oxide can be easily controlled as far as petrol engines are concerned using three-way catalyst. Reduction catalyst ensures that. But as far as diesels are concerned, such catalytic converters are not there. So you have to have different types of nitric oxide capture and removal mechanism, which are very expensive. So you have to go for after treatment or tailpipe gas treatment, which involve some chemicals like urea or ammonia, things like that, which are to be periodically topped and so on. So that's a big issue by itself. So the diesel engines will become expensive when we want to reduce the tailpipe emissions as per BS6. But BS6 is essential because nitric oxide is the pollutant which is causing respiratory distress. Of course, if you study the course on pollution control, you know this nitric oxide, in the presence of sunlight, reacts with atmospheric oxygen, ozone is produced, and asthmatics and other respiratory people with respiratory distress or illness, they will be very much affected and so on. Children will be affected. So BS6 is in fact a good thing, but we have to pay a price for it. The BS engines will be expensive.
Okay. Thank you, sir. Thank you so much, sir. Last question, final question, sir, from Pugal. Can you tell the different stages of combustion in CI engine?
Yeah. So this, of course, if you are a mechanical engineering student, you would have seen. So this is the diagram in which you can see. Can you see the slide? Can you see the slide? Hello?
Yes. Yes, sir. Yes, sir.
Yeah, the pressure versus crank angle diagram, if you look at, it shows that in diesel engines, the fuel is injected towards the end of the compression stroke. That means before the compression stroke is complete. When the compression is completed, then the piston will be a top dead center. But we are injecting the fuel few degrees before the top dead center. So that position is known as the start of injection time. So this is the position at which the first droplet starts entering the cylinder. You already have the compression stroke reaching its end. So high pressure atmospheric air or atmospheric air which enter at atmospheric conditions is pressurized to high pressure. So naturally the temperature is high. Now you see the pressure. So from the value of about say one bar or so on, it would have reached by this time somewhere around 35 bar. So at this condition, the first droplet enters. And injection is not an instantaneous one. You don't inject, let us say, 20 milligrams or 30 milligram of diesel as a single droplet. Actually, it's injected using an injector, using a fuel pump over, say, about 20 degrees crank angle or that 25 degrees crank angle. Accordingly, the start of injection is here, whereas the end of injection is here. So the duration over which the injection happens is about 20 degrees crank angle. Now the first droplet which is entering into the compressing charge, into the compressing air, will not instantaneously explode because it is a liquid. This liquid petrol should first break down. It will come out as a droplet. Even if the orifice diameter is say 0.2 mm, the first droplet that's come out could be say around 0.1 mm and so on. But 0.1 mm droplet cannot burn. So as it passes into the air, it breaks down into micron size particles. So these micron size droplets, because they are so small, they move with the air, pick up the heat, and they evaporate. And as they evaporate, they become vapor. And these vapors are mixing with, as and when they are formed, they are mixing with the air available and form a fuel air mixture. So the droplet getting broken down to tinier particles is known as atomization. And these atomized particles evaporating to form the gaseous vapor fuel is known as vaporization. And this vapor in turn mixes with the neighborhood air to form a combustible mixture. Mind you, this combustible mixture is already at the charge temperature. Because of the high compression ratio, the temperature could be as high as 270 degrees Celsius. But the property of the fuel, namely diesel, is that it can auto-ignite at 225 degrees Celsius. So without any spark, spontaneously starts catching fire. So this gaseous fuel air mixture catches fire. So that point is known as a start of combustion. So this delay period essentially is due to the droplet entering, physically getting broken down to tinier particles, evaporating, mixing, and after mixing, reaching the temperature of the auto ignition value at which the mixture will catch fire. So it's very small, millimeter cube or even small quantity, because it's the first droplet. But as this event is happening, we are injecting continuously up to this point. See, injection ending, okay? So the second droplet will be entering here, third droplet here, fourth droplet here, and so on. So the second, the subsequent droplets which are entering are facing an environment where already the combustion is happening. So because of that, what happens? Very rapidly these fuel particles vaporize, because vaporization is governed by the temperature. Higher the temperature, very rapidly the liquid will become vapor. So because the first droplet has already burnt and second droplet has burned, so beyond this point we have the temperature to be high within the cylinder. So these droplets are getting atomized, but at the same time very rapidly they vaporize. And after vaporization, they mix with the available air very rapidly, and because of the high temperature present, the chemical reaction taking place governed by the kinetics, the rate of the reaction is accelerated. So what happens if the first droplet is requiring, let us say, 5 milliseconds from the auto ignition temperature to get converted to product. The final droplets, the droplets which are injected during this delay period, at the end of the delay period, they may require only 2 milliseconds. So naturally what happens? Very rapidly, there are large quantities of droplets are burning, or large quantity of fuel is burning in the gaseous phase. So you get what is known as the uncontrolled pressure rise phase. And this is sometimes referred to as diesel knock also, because the rate of pressure rise is so large that this uncontrolled combustion phase is the first phase of combustion. However, the droplets which are entering during the uncontrolled combustion and after that, they encounter burning gases. Oxygen is not available, but burning gases are there. Oxygen is available, but it is in the end gas region. That means near the piston cylinder interface or at the farthest part of the combustion chamber. So the fuel injected will not reach the oxygen. So it takes time for the fuel injected to undergo combustion. So naturally, the steepness is getting reduced. So it becomes rather gradual pressure rise or even slight pressure drop. So this is the second phase. So this is the first phase is delay. 2 is the knocking or uncontrolled combustion. 3 is the controlled combustion phase, and with that it should stop. But if engines are designed poorly, then you may have even combustion during the expansion stroke, and that is a later combustion or expansion combustion, which is undesirable. So these are the 3 important phases of combustion: delay, uncontrolled combustion, and controlled combustion. And this is after burning we call.
Thanks a lot, sir, for spending your valuable time with us and giving very useful information about IC engines. Thank you, sir. Thank you so much, sir.
So shall I leave the meeting?
Jason?
Okay.
My greetings to all of you. I feel honored and privileged in getting this opportunity to propose the vote of thanks on this special occasion. First and foremost, I thank the Almighty for making this event possible. On behalf of Francis Xavier Engineering College, I would like to extend my sincere gratitude to the Honorable Speaker Dr. M. Udayakumar, Professor, Department of Mechanical Engineering, National Institute of Technology, Trichy, for accepting our invitation in his busy schedule and delivering such an informative lecture on this topic, testing of internal combustion engines. We have research scholars, professors and students as participants. This session will help them to carry their research work further. I extend my heartfelt thanks to the management, respected General Manager Development Dr. K. Jayakumar sir, and our beloved Principal Dr. V. Velmurugan sir for their moral support and tremendous guidance in conducting such a productive program. Finally, I would like to place on record my sincere gratitude to Dr. Joe Patrick sir, the head of the department, Dr. Jinatul Farida Abdul Ghani ma'am, Dr. I. Nidhimanikam sir, Mrs. Maheshwari ma'am, Mr. Ramkumar sir, and all our colleagues. Without their help and guidance, the program would not have been a grand success. Special thanks to our student Mr. Jason for his web screening support. This webinar was made successful only because of well-wishers, followers and participants of this event. Once again, I thank one and all. Stay home, stay safe.